morning, students. Now in the previous sessions we just see the pulse code modulation, right? Now what is a pulse code modulation? Now the signal, the analog signal is sampled and quantized and encoded into a sequence of binary data, right? So the analog signal is converted into a sequence of binary data through a sampling, a quantization and an encoding process. And we just see the decoding of PCM transmitter, receiver, decoder, encoder, everything, right? So what is the problem which we are facing in pulse code modulation? Now, when the sample signal is passing through the quantizer, so the quantizer output is a round off value. Now the quantizer output is a round off value means 1.8 will become 2, for example. So the sample value is going to the process of quantizer. The sample value is going to the process of quantizer, and a quantizer output you are getting 2. Means this 1.8 is round off to 2. Now they introduce an error of 0.2. Now that error is called as quantization error. Is it right or not? Now this is the sample value, right? Now this is the quantizer output. This is the quantized sample. So what is this quantization error? This is the sample value after sampling. Now this is the quantizer output. Now this is the quantization error. So can we say this quantization error, which is nothing but the quantized sample value, minus the original sample value. Now which is nothing but the quantization error is nothing but quantized sample value minus original sample value, right? Quantized sample value minus original sample value. Now you tell me, now when this error should be as minimum as possible such that this sample value, this quantized value should be very closed. So when this error is minimum, so these two are almost same such that your reconstructed signal will be same as that of the original message signal with a minimum error. So we have practically the quantization error should be as minimum as possible. The quantization error should be as minimum as possible. So we require the quantization error should be as minimum as possible. If you want a quantization error should be as minimum as possible, now what should we do? This deviation should be less. So you know that the maximum quantization error, which is nothing but delta by 2. So if you want a minimum quantization error, you want to decrease the step size. Now what is the step size? Now the step size, which is nothing but dynamic range by L. Dynamic range is a fixed range which we cannot change. So if you want to decrease the quantization error, step size should be decreased. If you want to decrease the step size, now L should be increased. Now what is L? A number of quantization levels. So if you want to increase the L value, you know that L, which is a function of n, because L, which is equal to 2 power n. Now if you increase the L value, which means n should be increased. When n increases, this L is increased. Am I not? So if n increases, what happens? If n increases, bit rate and bandwidth. What is the bit rate? 1 by Ts into n. What is the bandwidth? 1 by Ts into n hertz bits per second. So what is the meaning of that? Now while n increasing, which means bit rate is increasing. While n increases, which means bandwidth is increases. So it is not a good method. So in order to minimize the quantization error, whose effect will be increasing the bit rate and bandwidth. Now this is the disadvantage or a limitation of the PCM system. So in order to minimize this quantization error, now which will affect the increasing the bitrate and bandwidth. Understand or not? In order to minimize the quantization error, increasing the bitrate and bandwidth, which is not a feasible method, which is not an acceptable method. Why? Because when bitrate and bandwidth is increasing, the signal bandwidth is increasing, you cannot accommodate more number of signals, multiplexing is not possible. So the bandwidth and bitrate should be also as minimum as possible, but in order to minimize the quantization error, so this bitrate and bandwidth is increasing. But still the PCM, which is a very good technique, now this PCM is preferable when optical fiber cable is transmission medium. When optical fiber cable is transmission medium, now the best signal is the PCM signal is preferred. The PCM signal is preferred because now this PCM signal is transmitted with a minimum quantization error such that the bitrate and bandwidth increases. Not a issue because our medium is a fiber optic cable, a huge bandwidth. Understand or not? So therefore, now to overcome this limitation or this disadvantage, what is this limitation or disadvantage? Now my aim is to minimize the quantization error. No sir, I want to decrease the quantization error. I want to decrease this quantization error, but without changing the bitrate and bandwidth, without affecting the bitrate and bandwidth. So is there any method? Yes. Now there is only one method in a digital only PCM. There is a slight modification of that PCM, now which is called as differential pulse code modulation, DPCM. Okay. Now decreasing the quantization error without affecting the bitrate and bandwidth is now our technique. Now that is possible without decreasing the increasing the bitrate and bandwidth. In order to minimize the quantization error, we go for a differential pulse code modulation. Is a slight modified circuit of PCM. Okay. Now first you note on this. So now you understand what is the concept of DPCM. Now that we have to be implemented by a slight modification of PCM. Now see here. Now let us take one small example. Now this is a signal of 0 volts to 8 volts. Right? What is the dynamic range? The dynamic range is the maximum possible input to the quantizer and minimum possible input to the quantizer. The dynamic range, which is nothing but the dynamic range here, maximum possible input to the quantizer minus minimum possible input to the quantizer. The maximum possible input to the quantizer minus minimum possible input to the quantizer is called as dynamic range. Now in the case of, I am talking about PCM system. Okay, I am talking about PCM. You know this. So this is the dynamic range. Now this is the dynamic range, which is equal to maximum possible input to the quantizer is 8, minimum possible input to the quantizer is 8 volts. This is the dynamic range. So the same problem now in the case of DPCM. So what we are doing in DPCM is, now we want more correlation between the samples. Now this is 8 volts. Now one is maximum possible input, another one is minimum possible input in the case of PCM. So in a differential pulse code modulation, what is the concept is, so one input is 8 volts, let us assume. Now one possible input to the quantizer is 8 volts. Now another possible input to the quantizer is just a delay of TS seconds. Just a delay of TS seconds, which means this is that. Now let us take this is 7.2 something, 7 or something. So what is the here? Now here this is the dynamic range now. Now this is dr, dynamic range. So can I say this is one possible input to the quantizer, this is another possible input to the quantizer. If this is one possible input to the quantizer and this is another possible input to the quantizer, now which is nothing but with just a delay of ts seconds, this is one possible and this is another possible inputs to the quantizer. Therefore, now see here, there is a more correlation between the samples. Now which are the successive samples difference are applied to the quantizer or not? Just a successive sampling differences are applied to the quantizer. So now if you observe here, now can I say this is the dynamic range, which is nothing but, now here what is the dynamic range? Now here the dynamic range, which is nothing but, one is, let us take present sample value, another one is a previous sample value. This is the one is present sample value, another one is previous sample value. One is present sample value, another one is previous sample value. Now one is present, another one is previous sample value, or we call it as, now one is a direct sample value, one is a direct sample value, another one is a prediction of that. Okay, now this is the predicted sample value. Now with is a delay of how much? The predicted sample value with a delay of ts seconds. Clear or not? Now this is the dynamic range. If you take here the same example, now this is 8 minus 7.2. Now here the dynamic range, which is equal to, what happened now? The dynamic range is 0.8. Now here the dynamic range is 8 more. Now here the dynamic range is less. Now sir, when the dynamic range is decreases, what happened? Now you tell me. What is the maximum quantization error? The maximum quantization error, which is nothing but step size by 2. Now, what is the step size? The step size, which is nothing but, now what is the step size? The step size, which is nothing but dynamic range by L. Now the dynamic range is decreasing. Now you are not touching this without disturbing this L. L is constant. No, there is no change in L. Now dynamic range is decreasing. Then obviously the step size should be decreased. More correlation. So when step size is decreasing, now quantization error is decreases without changing the value of, without changing the value of N and L. Means without affecting bitrate and bandwidth. Without affecting bitrate and bandwidth, then you are decreasing the quantization error. Now this is the concept in the case of DPCM. Now this is the original in the case of PCM. Then you note down this concept. Now based on that, we implemented the transmitter portion and a receiver portion of a DPCM system. Okay, note down. Now we'll see. Now this is the analog signal, continuous wave signal. Now this is sampler. Now this is the sampler output. You know that the sampled signal. Now this is the sampled signal. Now here I am taking an adder. Now this is the subtractor circuit I am taking here. Now one input is a sample signal and another input is a predictor. This is the prediction filter. Now see here, let us take this is a x cap of NTS is the predictor output. Now this is the quantizer. Now here also I just take one adder. Now this is the quantizer output. And this prediction filter output is connected to this adder. Now these two addition will be as input to the prediction filter. Anyway, we'll see. Now this is the error signal, right? Now which is the sample value minus predicted output. So now let us take. Now this is the error signal. Now the error signal, which is, this is the original sample value E of NTS, which is equal to sample value minus predicted sample x cap of NTS, right? Now this is some quantization error which is adding here. Therefore this is quantized error signal. This is the quantized error signal. Now see here. Now some quantization error is adding, and this is the quantized error signal. Now this is the predicted samples. Now here I write, this is x can of t is a predicted sample value. Now you see here, now this is a quantized error signal. Now this is error signal. Now it is going for quantization, quantized error signal. The quantized error signal QE of NTS, which is equal to E of NTS plus some quantization error, then some quantization error which is added to you. Okay. Now this is some quantization error. Now this is the quantization error. This error is going for quantized, and this is the quantized output. Now which is nothing but the error signal plus some quantization error. Now let us take this is QE of NTS. Okay. Now quantization error. Okay, note down this. Now see, this is error signal. This error signal is going for quantization. So this is a quantized error signal. We can write like this, EQ. Error signal is going for quantization. Therefore, this is quantized error signal. So for in order to avoid the confusion, now this is error signal is going for quantization. Therefore, quantized error signal. Quantized error signal. EQ of NTS. Now this is some error is added because of this quantization process is called as quantization error. So now we'll see this is the here input to the predictor. What is the input to the predictor which we are going to be find? The input to the predictor which is nothing but now this predictor output and this a quantized error signal which is are added. Now this quantized error signal is going for the process of encoding, encoder. Now this is nothing but an n bit A to D converter, right? You know that same PCM. So now due to this n bit A to D converter, now this quantized error signal is going to digital binary data which is nothing but differential pulse code modulated signal, DPCM signal, which is a differential digital data, right? Now here the important thing is you see here what is input to the quantizer. I already explained in previous concept. The input to the quantizer, one is the present sample value and another one is the predicted sample value. So the difference between a present sample value and previous sample value will be very small. So which is going for input to the quantization. Clear or not? Now in the case of PCM, now one is present sample value, another one is previous sample value. One is present sample value, another one is maximum value, another one is minimum value in the case of PCM. Then you understand the circuit will be same indicating or not. So the input to the quantizer in a case of PCM is dynamic range, maximum possible minus minimum. But the input to the quantizer in the case of DPCM is one is a present sample value, another one is a predicted sample value. The predicted sample value is the sample value with a delay of TS seconds, such that this dynamic range is very, very small. Now this quantized error signal is going for the encoding process and a staircase approximated signal which is nothing but a sequence of ones and zeros. Now this is the DPCM signal. Okay, now done. Now let us take this input to the predictor is XQ of NTS. Now let us take easily. Now first you understand the concept. Oh, here is the concept you can easily understand. Now what is the dynamic range? Present sample value minus previous sample value. One is present, another one is previous. Or one is present, another one is predicted. The predictor is nothing but a delay of TS seconds. That's why I'll take every time it is TS seconds. Now see here, this is the original sample value. These are the original sample values. Now the original sample values are undergoes the process of sampling and this is the sample value. Now this is the sample value and with a delay of TS seconds, this is the predicted sample value. Now the original sample value minus predicted sample value is nothing but the error signal. Now that error is going for the quantization process. Now this is the quantized error signal. Now the quantized error signal is the error signal plus some quantization error. Okay. Now that is going for the encoding process, and this is added, and this is the input to the predictor. Now we'll see input to the prediction. Input to the predictor. The input to the predictor, which is xq of NTS, the input to the predictor signal, input to the predictor, which is xq of NTS, which is nothing but x cap of NTS. This is the input to the predictor xq of NTS, which is nothing but x cap of NTS plus the quantized error signal EQ of NTS. Now see here, x cap of NTS, which is nothing but x cap of NTS plus, can I write like this? Now this is EQ of NTS. Now what is EQ of NTS? EQ of NTS, which is nothing but E of NTS plus QE of NTS. And we know that now what is error signal? E of NTS, which is nothing but here. Now that also we can replace. So this is the predicted signal plus E of NTS, which is nothing but x of NTS minus x cap of NTS plus quantization error of that particular sample. Now here this x cap of NTS is cancelled. Now this is xq of NTS. Now this is xq of NTS. Now the quantized sample value, the quantized sample value or input to the prediction, which is nothing but x of NTS, then this is nothing but, now the x of NTS is the original sample value plus some quantization error, So this is the actually input to the prediction. Okay. Now what is this? This is the actually input to the predictor. The input to the predictor, input to the prediction filter xq of NTS, which is nothing but now the original sample value, with some quantization error, which is nothing but the original sample value with some quantization error, which is again this x cap of n, which is applied to the prediction, and this is the sample value. Now see here, x of NTS, the original sample value plus or minus some quantization error, because this error is going for the quantization process. Now this is nothing but the original sample value. So when this quantization error is here is a very simple. When this quantization error is as minimum as possible, such that now this original sample value and this predicted sample value, it should be very, very, very small. So the quantization sample value and the original sample value will be very close when this quantization error should be as minimum as possible. Okay. Now this is the quantizer, input to the predictor. Okay, this is going for the predictor. Now this is the predicted sample, and this difference is error, quantized error, and this is going for encoding process. Okay, no doubt. Now this is the DPCM signal. Now this is the DPM signal output, this is a decoder, then this is nothing but a quantized, exactly the reverse operation. Now this is the quantized error signal, right? The quantized error signal or staircase approximated signal. Now this is, now there we are subtracting here for minimum quantization error or a minimum differences. Now here we get the original values added. Now the same kind of the predictor what we are using, we use the same predictor. Now this is nothing but now the quantized value, which is nothing but input to the predictor. Same, you should be get the same. Now let us see here. Now the predictor output is nothing but the predicted sample value x cap of NTS. Now see here. Now this is the predicted sample value and quantized error signal is the output of the decoder. Now which is nothing but input to the prediction. Now this is the predicted sample value. Now see here, the predicted sample value or input to the predictor is nothing but the original sample value with some small quantization error, means it's a original sample value only. So finally what we can say is the input to the predictor, see here, the input to the predictor which is nothing but the original sample value only. The input to the predictor is nothing but a original sample value with some small quantization error. When this quantization error should be as minimum as possible, yes, this is minimum because this successive difference will give the minimum error. So when this is minimum, now this is approximately same. When the original sample value, this quantized sample value, which is all are same, so then this sample values are applied to the reconstructed filter, which is nothing but a low pass filter when a sampling rate is greater than 2 omega samples per second, then this is the original analog signal with the minimum quantization error. Understand or not? So what is this XQ of NTS? Now this XQ of NTS is the quantized sample value or input to the predictor, now which is nothing but EQ of NTS, EQ of NTS, now quantized error signal plus now the predictor output x cap of NTS. Now this is the quantized sample value, this is input to the predictor, right? This is the input to the predictor XQ of NTS, which is nothing but EQ of NTS plus x cap of NTS. Now see here what is EQ of NTS. Now you may write like this. This EQ of NTS is nothing but E of NTS plus, or you can write it here, E of NTS, which is nothing but X of NTS minus X cap of NTS also. Okay. So this is the quantized sample value. Now finally you can get the answer here is also XQ of NTS, which is nothing but the original sample value. See here. Now if you are simplifying this again, what we are getting? The same. XQ of NTS. Now the final answer is XQ of NTS, same. Now see here, this is XQ of NTS, which is nothing but X of NTS. This is X of NTS plus some quantization error. Some quantization error. That is the final answer. Now the same signal. Now this is the input to the predictor or a quantized sample value of the predicted value, then which is going for the low pass filter for the reconstruction purpose, and you will get the same signal as the original signal. Now both are, now this is the DPCM encoder, DPCM transmitter. Now this is the transmitter portion, DPCM transmitter, and this is the DPCM receiver. No doubt. Okay, this is DPCM encoding and this DPM decoding process. Okay, now just explain once again finally, then you just try to concentrate here. This is the original signal, which is the analog signal, is going for sampling. Now therefore this is the sample signal. The successive time difference between each sample is TS seconds, right? Now these are the sample signal. Now here I'll take a predictor, which is nothing but the predicted samples. For example, your convenience, you can take it, this predicted sample is just a delay of TS seconds. The original sample with a delay of TS seconds is nothing but a predicted sample, or let us assume previous sample. Now see here, this is the predicted sample. X cap of NTS is the predicted sample or a previous sample. So now what is the input to the quantizer? The input to the quantizer is the original sample value minus predicted sample value. The input to the quantizer is the original sample value minus predicted sample value. So this is the input to the quantizer. I just assumed as input to the quantizer is the original sample value minus predicted sample value is nothing but some error. The original and original sample value and previous sample value is some error. Now that error sample value is going for the process of quantization. It is a round off process. Therefore this is the quantizer output. But this error is going for the quantizer, therefore quantized error signal, or which is output of the quantizer is a input to the quantizer and some quantization error is added. So this is the input to the quantizer is the original sample value minus predicted sample value difference plus some quantization error. Now this is the quantized error signal is going for the process of encoding, and this each quantized error signal is converted into n number of bits. Okay, now what happened here? Now this same quantized error signal which is going for an encoding, now which is added with the predicted sample values, and those two are added and which is applied to the input to the predictor. Now this xq of NTS is the input to the predictor. Now the xq of NTS is the input to the predictor, which is nothing but a predicted sample value with a quantization error sample value, quantized error signal. So now see here, now what is the input to the predictor? Your doubt is, sir, what is predictor? What it will be fed by predictor? So predictor feeding is what, sir? So that is I'm saying here predictor feeding is nothing but the input to the predictor is nothing but x cap of NTS plus EQ of NTS is a quantized error signal, which is nothing but quantization error plus error signal. Quantization error plus error of the original and minus previous sample value. So again I can write it. Now this x cap of NTS, E of NTS is nothing but now x of NTS minus x cap, and this is cancelled. So what is finally the predictor input, which is nothing but original sample value with some quantization error. Now let us take, my question is, quantization error is 0, ideal case. If your quantization error is 0, now the quantized sample value, which is same as that of the original sample value. The quantized sample value, which is same as that of the original sample value, now which is nothing but the original signal and that quantized sample value. Now both will be same. The input to the predictor is nothing but the original sample value. So again this is the original sample value. In this way also original sample value. The difference is 0. No, the difference is 0 means error is 0. Ideal case, when error is 0, now which means that now this is the, if error equal to 0, whatever the sample, the same thing will be coming here and which is going for the process of encoding. But let us introduce this error, but with a small error, minimum error, because now the correlation between the samples are very less. When more number of samples are correlated, then obviously the error will be decreased. Okay, and now this is the DPCM signal, now which is going for the decoding process. Now the output of the decoder is nothing but this is the quantized error signal, and don't worry, a quantized error signal is nothing but now quantized error signal is nothing but original sample minus previous sample plus some quantization error. So finally the students are asking that, sir, what is the signal which is going for the process of quantization? Tell me, the students. Which signal is going for the process of quantization? Is a original signal or a sample signal or a quantized sample? No. This is present. Listen carefully. This is present. This is previous. The present will not go to the quantizer. Previous is also not going to the quantizer. Present minus previous, this gap. This is the present signal. This is the previous signal. Now these two are having a difference of TS seconds. That difference is going for the process of quantization. Now that difference value, let us take 0.8. Now that is round off to 1. Understand or not? So when this difference means this is not maximum, this is not minimum. This is one sample. This is just a delay of TS seconds. This is one sample. This is just a delay of TF seconds. Now as successive samples difference is going for the process of quantization, that obviously the error should be as minimum as possible. Understand or not? Now that is the concept of DPCM. Now where error should be less, such that without changing the bitrate and bandwidth. So we are not disturbing the n value. Therefore, now this bitrate and bandwidth of DPM signal will be same as that of DPM signal will be same as that of that PCM system. Okay? No doubt.